Dan is has been at SIO since about 1994. He received his bachelor's degree in physics here at UCSD, came to be a UCSD or SIO graduate student, completing his PhD in about 1987. Then he went on then to do a postdoc at Woods Hole, was on the faculty of the University of Washington, was recruited back to SIO as an assistant or associate professor, and has now just been promoted to full professor as of July 1st. The subject of Dan's talk, as I've already said, is having to do with ocean fronts and weather. Fronts and eddies, the weather of the ocean. So Dr. Dan Rudnick.
Thank you. Well, first I'd like to say it's a pleasure to come here and speak at the aquarium. It's something I've never done before, and I'd like to see how it's going to go. But first, let me say that what I do is I do physical oceanography. Physical oceanography has to do with the physical processes in the ocean. I look at the currents, I look at the temperatures, the salt content, that's the salinity, and try to understand basically the physics of how the ocean works. The topic I'll be talking about today concerns fronts and eddies, the weather of the ocean. Well, just as there are fronts in the atmosphere, which you all know about, there are also fronts in the ocean. Fronts in the atmosphere you can see basically every day on the evening news when the weatherman shows you his satellite picture, and there are clouds on one side, no clouds on the other, often a strong change in temperature. In the ocean, fronts are separate regions also of different temperature, but the other component that determines the properties of the water, the density of the water, is salinity. So the salt content can also change. Let me show you here a satellite picture, a visible satellite picture of the United States, and you can see the clouds on one side of a very strong front. Here I am, I'm a weatherman now. Extending from the Great Lakes down to Texas, there's a very strong front, in which you can see, and you'll expect to have rain on your picnic. Now, on the other hand, in the ocean, we don't have that problem of predicting whether you'll have rain on your picnic, but we do have fronts in the ocean. And here's also a satellite picture. This is a satellite picture of sea surface temperature, and the way one looks at this picture is the very red colors are warm, the blue colors are cool, and you can see that there are strong changes. For example, there's a front right there that's cold on this side and warm on this side. And you might be able to pick up some other fronts, say across here. And there's some things that look like they might be little eddies, little storms in the ocean, like right here, where there's a swirly kind of thing. And as you look at this picture, you can see all kinds of structure in the ocean. And I guess one of the points I'd like to get across today is, as you look out at the ocean and you think it's kind of a very smooth and uniform thing, it really isn't. There's structure everywhere that you look in the ocean. Sometimes you can look out, for example, from here, although I don't know if you can today, and you can see stripes on the ocean, and these are fronts. So, let me tell you one other way that mariners for a long time have identified fronts in the ocean. When you look out on the ocean, sometimes you'll see long lines of debris, seaweed, flotsam, jetsam, oils sometimes that are floating on the water will collect in these regions. And here's a couple pictures of floating debris on the surface of the ocean. And the reason one sees this debris on the ocean is because fronts are often regions of convergence, where the water comes together like this at the surface and then plunges down. Everything that's floating on the water will then be sucked into this region of convergence, and you'll see these lines. On either side of this front, there's probably a strong change in temperature, maybe of salinity as well. Fishermen know about these. And in fact, they search out fronts because they're also regions of strong biological productivity. So fishermen know about fronts. They often fish there. And I'll try to explain why they fish there, why these regions of convergence at the surface often also are regions of strong biological productivity. Well, I've showed you a little bit of what the ocean looks like really from the surface only. I showed sea surface temperature, and I also showed the convergence lines of flotsam and jetsam on the surface. But what we really want to do when we do oceanography is look at the ocean throughout as much of the depth as we can. And so this is one of the ways we have looked at the deeper ocean and have surveyed fronts. It's the seesaw. It's a towed vehicle. We tow it with a cable that goes all the way up to the ship. And this picture here shows more or less to scale what it looks like. Here's the ship right here. There's a cable down to the seesaw which is being towed. We tow it at about 8 knots. It's about 8 miles per hour. And the thing that's different about this compared to an airplane is if you look at the wings are upside down. And the reason the wings are upside down is because the lift, so to speak, needs to be downward to get this thing down into the water as we tow. Any of you who've gone fishing and maybe tossed out a jig to troll knows that what it wants to do is mostly go to the surface, and the challenge is to get it down deep. The reason it goes to the surface is because there's a great deal of drag on this cable. And so what these wings do is they overcome that drag and try to push the vehicle down. Now we can control the pitch of these wings from the surface, and by changing the pitch like this, we can make the vehicle fly any kind of path we want. So we load this up with different instruments to measure, say, pressure, temperature, salinity, some optical properties like fluorescence and others, and then we tow it through the water to make measurements in the upper ocean, say the upper few hundred meters.
Who designed it?
This instrument is a very old design that dates back to some Canadians, I think, in the 60s or 70s. As you can see, it doesn't look very streamlined. It doesn't look very fancy, and in fact, it isn't. It's an extremely old design. This instrument here was made by Chelsea Instruments, which is a company in the UK. So let me show you what happens when we tow this instrument through the water. But first let me show you what the operations look like on board ship. To deploy an instrument like this, what we do is we put it through the A-frame on the ship. That's this device right here. And you can see us with lines all over the place. I think in this case we're actually recovering it after it's been in the water for some time. One of the challenges of towing a cable through the water, this is the cable right here, is its drag. What we do to reduce the drag is we put a rigid plastic fairing on it, and essentially we're towing this seesaw with a very long, almost a several hundred meter long wing. And it takes us a great deal of time to take care of this fairing. Each piece of this fairing is a rigid plastic piece about this long, and each one of these things has 4 screws, and we have 700 meters of that. So you can imagine what kind of effort that entails. Because we have this special cable and fairing, we need a special winch, and here we are taking care of our winch. Well, then we go ahead and we tow the seesaw, and this is what a trace looks like as we tow it along. The plot here has on one axis time, and on the vertical axis pressure. Now let me tell you something we oceanographers know about pressure, and that is I'm measuring pressure here in decibars. That's 1/10 of an atmosphere. It's a very fortunate fact that 1/10 of an atmosphere is about equal to a depth of 1 meter. The weight of 1 meter of water gives you a pressure beneath it of 1/10 of an atmosphere, and that's good to better than 1%. So the way we measure depth in the ocean is by measuring pressure, and we often interchange decibars and meters for depth freely. So when you look at this picture, you can look at this number, say 300, and know that that means 300 meters depth in the ocean. So what we do as we tow the seesaw along is it goes up and down, in this case from very near the surface to about 320 meters. We're towing the seesaw at 8 knots. So 1 hour here, we've moved 8 miles, 8 nautical miles, and we've done about 6 cycles from the surface to deep. And as we're towing along, we're measuring a variety of parameters. And our watches at sea are typically 4 hours. So this is half a watch. And whoever thinks this is a very interesting plot, raise your hand. I can see nobody did. And that's the idea. That's basically the idea, is this is, when we're using it, it works very well. It's extremely boring because it keeps doing what it's supposed to do and we don't have to do anything else. And this is half your watch, and then you can watch the same thing happen again for another 2 hours, and then you can go get some lunch. So this is how we collect the data. Let me show you what the data then looks like. This is a survey of a front. We made this survey by taking our seesaw and driving it back and forth in a series of profiles across the front. There's about 8 to 10 profiles across the front in this survey. If you look at the axes, I've plotted them in longitude and latitude. If you know your geography, you would know this is just south of the Azores in the North Atlantic. This is a feature that's been known to oceanographers for some time. It's called the Azores front, but this is a very small piece of it. The picture I'm showing you is about 200 kilometers by 200 kilometers, but what you see is cool, dense water on one side of the front, warm, less dense water on the other side, and a fairly sharp front in between. Now, all the pictures I showed up till now have been of the surface. This one is now at 68 meters depth. So this was only possible by doing a survey using an instrument like this, or others could do the same thing. So you see a very strong front, and now I'm a weatherman in the ocean, and I can say here's a front just south of the Azores. If you're living down here, watch out for this one. Now we can also measure velocity, currents from the ship. We measure these currents using an instrument, an acoustical instrument that pings, and then by the Doppler shift of the returning ping, it can measure the velocity relative to the ship. And then by having some navigation, we know where the ship is and how fast it's going. We can get the velocity, and what you see here is there's a jet. There's a strong flow going more or less right along the front. Weaker flow on either side. This strong jet along the front is a very typical feature. It's one of the simplest kinds of dynamics we see in the ocean. The term for this dynamics is thermal wind. We've picked up this term really from the meteorologists. For example, they know, and we know too, that if you have a front that's cold on one side and warm on the other, there will be a wind in between that goes in between these warm and cold on one side and the flow in between. This has been called thermal wind. Even though this is not a wind, this is a current, we use the same term in oceanography. This is a graphic picture of this thermal wind, the flow along the front. So now let me show you what this front looks like as a function of depth. This is a section, a north-south section across that front. It was made now by the seesaw going up and down lots of times. And the vertical axis here is depth from the surface to 350 meters. And the depth I showed you before was 68 meters, which is right around there across here. Again, the red colors are warm and less dense. The blue colors are cool and more dense. And you can see here's the front extending down. This also shows some very standard features of the upper ocean. First off, there's a region up near the surface where you can see the colors are fairly constant. This is called the surface mixed layer of the ocean. In most of the oceans, especially during winter, there's a surface layer that's mixed by the wind and by storms that come through, and this layer is uniform in things like temperature and salinity, and it's a very turbulent layer. Beneath, you can see all the lines and the gradations of colors as you go deep. This is a stratified region that's called the thermocline. At the base of the mixed layer, you can see a region that's extremely stratified, and that's also quite typical. Now, there's one feature in this plot I'd like to point out especially, and that is, as you can see, there's this kind of yellowish water, and it appears like there's a tongue of this yellowish water that's drawn down here. And this is due to the fact that at fronts there tends to be very strong vertical circulations, with the flow going down on the dense side and the tendency for the flow to go up on the less dense side. This happens also in atmospheric fronts, and it's the reason atmospheric fronts are associated with rain. Rain is associated with updrafts of air. Now, in the ocean, this is extremely interesting because these vertical circulations down on this side and up on this side turns out to be very important for the plankton in the water. In fact, plankton take advantage of these vertical circulations in ways that I'll explain later. Now, this particular front, you can see that there's very strongly sloping surfaces here, and this front extends down to something like 1,000 meters. Well, here's another section in the ocean. This one is very much longer. It goes from 25 to 35 north in the North Pacific. This is about, it's at 140 west, which is about halfway between here and Hawaii. We went out to this area of the ocean in the middle of winter, and you can see in this picture there's a very deep mixed layer again that extends down to about 100 to 150 meters. Now let me tell you why we went out to this place. The reason we went out in the middle of winter to this place is because I wanted to look not only at a single front, but I wanted to look at the statistics of fronts. I wanted to see, well, if I move along in the ocean, what is typical about the kinds of horizontal structures that I'll see? And to do that, what we did is, after getting this section, we towed the seesaw here at a depth of about 50 meters horizontally, and we tried to keep it very level at a constant depth. Now, in the middle of the North Pacific in winter, I don't know if any of you have been out in the middle of the North Pacific in wintertime, but it's not a very calm place. It's a place with waves constantly and wind and rain, and life on board the ship is kind of bumpy. In fact, you're moving with the waves, which are going to be up to 10 meters quite typically. But what we want the vehicle to do is to stay quite stable and at a certain depth. Well, we were successful even though we were moving at 10 meters up on the ship. The vehicle down here was moving only by about 1/3 of a meter. And so that was something of a challenge for us, and I think there were a number of people on ship who would have rather been on the vehicle. So let me show you what we found by making this tow. And well, to me this is very interesting, but what we found is I can, by making a very long tow like this that also resolves very small horizontal scales, I can focus in again and again and again and look at all the different structure in temperature and salinity. And I got to tell you something before we talk about this plot, and that is that physical oceanographers just love temperature and salinity. We're crazy about it. And the reason we're crazy about it, there is a reason, is because most of what we know about the large-scale circulation of the ocean has been learned by oceanographers going out and measuring the temperature and salinity and looking at the patterns. And by looking at at traces of temperature and salinity in their patterns, they can see where the water comes from because, well, salty water comes from here, and we see salty water here, so that must be where the flow is going. And so through the years, we oceanographers have just studied temperature and salinity to death, and here we're doing it again. Now what you see in these series of panels is the upper panel is the total length of the tow from 25 to 35 north. That's about 1,000 kilometers. You can see the distance on the top axis. What I've plotted here are temperature in blue and salinity in green, and you can see there's a series of fronts and dips and wiggles. And the interesting thing about these fronts and dips and wiggles is that temperature and salinity are dipping and wiggling at the same time, in the same place, I should say. And each succeeding panel now is a blow up by a factor of 10 of the region in gray above. So this goes from 32 to 33 degrees latitude. That's this region right here. And you see that on a scale of about 100 kilometers, that also you can see dips and wiggles in both temperature and salinity. The next panel down is about 10 kilometers across, and you can see on a kilometer scale then dips and wiggles in temperature and salinity that are quite correlated. And finally, you can see down at the smallest scales that are visible here, which are on the order of tens of meters, temperature and salinity are quite strongly correlated. Now, they're correlated in a special way. That is, if you look at one of these dips, it's hot and salty on one side and cold and fresh on the other. And that turns out to be very typical. We call this phenomenon compensation. It has actually been known for some time, although only very recently did we learn that it happens down to the smallest scales. Question? The question is, are the minerals that cause salinity constant in proportion?
Right.
Yes. And that's an amazing but true fact in the ocean, is that the composition of salinity stays remarkably constant. If you look at these, they're, as I said, warm and salty on one side, cold and fresh on the other. And this is remarkable because these two components determine the density of seawater. Cold water is dense, warm water is less dense. Salty water is dense, fresh water is less dense. And in fact, because it's warm and salty on one side, cold and fresh on the other, these two effects counteract each other so that the density contrast across these fronts is made smaller. So this tells us something kind of interesting about the way the ocean stirs and mixes. It stirs and mixes in such a way to make temperature and salinity compensated and to keep density contrasts relatively small. This mixing of the ocean in this way is a very important property that eventually will have effects on the largest scales, on climate kinds of scales. This is why we study mixing in the ocean. So let's talk about something a little different just for a moment. This is a picture, a photograph from the space shuttle. It's actually a photograph. And this was given to me by Walter Munk, who's been looking at these features recently. What you can see are a series of spirals. And the interesting thing about these spirals is they're all spiraling in the same direction. What we oceanographers would say, well, are counterclockwise. We call that cyclonic because it's the same direction that the Earth spins. Well, you've all heard of cyclones, right, in the atmosphere. Well, these are cyclones in the ocean. As you can see, they're not that big in size. This scale is 8 kilometers across, but it turns out that they're quite prevalent. In fact, when Walter Munk looked at all these pictures that he could find of these spirals, he found they were overwhelmingly cyclonic, overwhelmingly counterclockwise. In fact, just like tornadoes are overwhelmingly counterclockwise. And we're just beginning to learn about these cyclonic spirals in the ocean, But it's enough, I think, to say that this is the weather of the ocean. If you were a plankton living in the ocean, you would see these counterclockwise spirals. I should have said this is the northern hemisphere, and they spin the opposite direction in the southern hemisphere. And in fact, these cyclones are features of the ocean mixed layer that I showed you. And if you recall, the ocean mixed layer was something like 100 meters deep, and from what we can tell by measuring these things from ship, that's how deep they go. But we're just beginning to learn about them. The fact that you can see them actually is because the sun is glittering off the surface, and these striations are changes in the surface roughness of the ocean, really due to convergences and concentrations of oils and surfactants on the surface of the ocean. Now, I promised I would talk about the effect of fronts on biology. This is a section that's right off of San Diego, a little ways out. And again, the vertical axis is pressure. You can think of that as meters. And the horizontal axis is kilometers. This was done in the fall. The mixed layer in this case, which you can see here, and is down to about 50 meters. The colors in this case are a measure of fluorescence, a measure of the chlorophyll in the water. Now, there's a very typical feature shown here, and that is that if you look vertically, you see there's a maximum in chlorophyll at a depth typically beneath the surface. This deep chlorophyll maximum is typical. The reason you have more chlorophyll at depth is because the growth of plankton is controlled by two factors, as are the plants in your garden. One is light. Plants need light, and plants need nutrients, fertilizer. It turns out that, as you know, light should be strongest at the surface, it's sunlight. But nutrients are in greater concentration at depth, because when the nutrients are brought near the surface, the plankton consume them. So at a place where the plankton can receive both adequate light from above and nutrients from below, there's a maximum. Now, the other thing you see is these lines here are lines of constant density. As the lines of constant density move to the surface, this is an indication of upwelling. And when you see the upwelling, you also see a bloom. You see kind of darker red colors. That means more chlorophyll. The reason there's a bloom is because some of the nutrients, the fertilizer essentially, is brought up from below. It's brought near to the surface where it gets sufficient light, and then you have a bloom. So these vertical circulations that I discussed at fronts are extremely important for phytoplankton in the ocean. And you typically see phytoplankton blooms at fronts. Now, once you have phytoplankton bloom, all of the other organisms that feed on phytoplankton will gather, and this is why fishermen fish at fronts. And most of what I've shown you is out in the open ocean. In fact, this is very far from the coast. But there is also upwelling near the coast, coastal upwelling, which is extremely important. And there are these kinds of fronts, most of which I've shown you have been far out into the open ocean. So I've discussed a little bit about what we know about fronts. And let me close now by discussing two new instruments that we're going to use in the coming years to learn even more about the upper ocean. The first is this device here. It's called the underway CTD. And what we wanted to do is basically make the same kinds of measurements we're able to make with the seesaw. But as you saw, the seesaw is quite an operation. When I showed you the pictures, we needed a big A-frame, we needed a winch, we had this fancy cable. But I wanted something where you could do the same thing and pick it up like this. And here's an instrument. It's called an underway CTD. And I have a kind of a picture here to show what it might be able to do, or what it can do, actually. There's a ship, and many of the ships that are available to us can move very quickly. In fact, if we can make something work at 20 knots, we can use container ships that are moving across the ocean. We don't have to take out one of our own. So the goal here is to get something to go down, to profile down to about 150 meters while a ship is moving very quickly, 20 knots, and in fact this can do it. And the way this works is essentially you toss this off the back of a ship. It's got sensors to measure pressure, salinity, and temperature, and as it falls, it leaves this line behind. And as you're traveling on the surface of this, on the ship, on the surface, you have a winch that's spooling out line behind you. Now this is a wonderful thing, because by spooling off the probe and by spooling from the ship at the same time, the line is not pulled through the water. So we can get arbitrarily deep. Otherwise, if we tried to tow this thing, it would want to go right to the surface. So, well, we can get it down to a depth like 150 meters, we proved. Now, the problem, of course, is then getting it back, because now you really do have to tow it, and the tensions will get quite high. But there's a wonderful effect. It's called the water pulley, and it's as if there's a pulley right here. And what happens is as we tow it back in, it follows the path right like that. And you can demonstrate this to yourself if you have a piece of line and you take it and put it in some water and you move it through like this. It goes like a snake. It follows itself. And by following itself like that, the tension is very low, because the tension of a line moving through the water like this is much smaller than the tension of the line moving through the water like that. So this is the underway CTD. It's in development now, and we hope to have it on a variety of ships over the next several years. In fact, I'm trying to make it small enough that even somebody with a yacht, for example, who would want to help us out and make some measurements when they're going to Hawaii, could go ahead and make some profiles. Question?
Any idea what the cost of that is going to be, production?
Yeah, I have a pretty good idea. This probe here, we expect, should cost between $1,000 and $2,000 and should be reusable until it's lost. This is an instrument being designed at Scripps right now by Russ Davis and Jeff Sherman. It's called a glider. And I guess there's a theme here that we like to fly in the ocean, and this glider does just that. In fact, what it does is by changing its buoyancy, it goes up and down in the water, but while it's going up and down, it glides on these wings. As it's gliding up and down, it essentially can do the same kind of path that I showed you with the seesaw, up and down from the surface. This potentially can go as deep as 1,000 meters. As it's going, it can measure pressure, and there are a couple probes here for temperature and salinity. And this is fully autonomous. It's not attached to the ship in any way. We put it out. It will go down, up and down from the surface to as much as 1,000 meters. It can do up to 1,000 of these cycles and go as far as, I think, 6,000 kilometers. Now, as it's doing this, it makes its measurements periodically. It can come to the surface, and there's an antenna in one of these wings, and it can send the data back by satellite.
What's the propulsion?
It all works on buoyancy. So what you can't see in here, there's an open chamber right here that has a bladder. The bladder can fill with oil from the inside. So by filling with oil, it changes its volume and therefore its buoyancy. So now as it changes its buoyancy, it goes up and down. Now as it's going up and down, then it just glides, just like a glider. The way it steers is the same way a hang glider steers, by changing the center of mass. Their battery packs in here are the heaviest thing, and we move the battery packs fore and aft and side to side. So this is the glider. It's under development now really not by myself. I'm trying to do my best to explain somebody else's work, but by Russ Davis and Jeff Sherman, and a number of us are very excited about using this instrument. And perhaps later you can come up and take a look at it.
What controls rolling?
We can move the battery pack side to side as well, and control the center of mass this way as well as this way.
Are they gel cell batteries?
No, they're lithium.
What's the battery life going to be?
It depends on how much you drive. It's limited by the number of cycles we run. And when I say it can do about 1,000 cycles, that gives you an idea of what we're able to do. Oh, how long?
Days, maybe?
Well, if I do 1,000 cycles in a few days, I get a few days. If I do 1,000 cycles in a year, I get a year.
Would it fail safe or rise by itself if you lose the batteries?
No, it's neutrally buoyant.
Stay there.
It will work. These things are based on some floats that are out in the ocean right now that have been in use basically since 1990. And these are the Alice floats. They would profile vertically from the surface to 1,000 meters, making measurements of temperature and salinity, but they wouldn't glide. We know from experience that those things work fairly well. So the new thing here is to get it to glide. So we're fairly confident that these things will last. But yes, they do eventually get lost. At the end of their life, we do not recover. It won't float.
What's the glide angle and speed?
It's a good question. What's the glide angle and speed? The glide angle is, the speed is 25 centimeters per second. And a typical use would be, say, to complete a cycle in 6 kilometers in the horizontal down to 1,000 meters. I think it's about 20 or 30 degrees. And there was one question about, will these things get lost if they fail? If they fail, they do get lost. But we plan their missions so they return before the batteries die. So in typical use, we hope to get them all back. So let me conclude. Just to summarize what we talked about today, we talked about fronts and eddies, and I hope I convince you that they're fairly prominent features in the upper ocean. This weather does have very strong effects on biology. I've talked about some of the observations we've made using ship surveys, an instrument like the Seesaw, and I hope I've given you a taste of what things we plan to do in the future with these two new instruments. Thank you very much. The question is, what satellites will we use? The satellites that we will use for communications are put up commercially. The question is, can I discuss the anatomy of upwelling? Upwelling is typical along many of the coasts of the world, not just San Diego. The way upwelling works near the coast, essentially, is the wind blows the surface water offshore, and water then comes up from deep to replace it. There is a very strong front often between the cold water that's been upwelled and the warm water that's further offshore. So that's the basic dynamics. And it is true that this happens throughout the world, not just San Diego. The question is upwelling a difference in temperature? Well, the term upwelling, this term we use mostly, has to do with the vertical motion of the water. Upwelling means water coming up from depths. But often it is associated with very strong changes in temperature because the deep water is colder. The question is, does the water come up from 5 miles down? And the answer is no, it doesn't come from that deep. But we do know about where it comes from. Typically, it's coming from depths of 100 to 200 meters.